Good morning, viewers. Today I am going to talk about a very important topic in inorganic chemistry, that is crystal field theory, and it is basically included in the BSc level syllabus. Now, before crystal field theory, we have a valence bond theory. Okay, so in valence bond theory, we have some drawbacks. That is, it can only say about geometry, it can say only about magnetic properties of coordination complexes, but it cannot say about the electronic spectra, it cannot say about the colors, and why some ligands form high spin complexes, why some ligands form low spin complexes. So it cannot say. Therefore, to overcome these drawbacks, two physicists, that is called Hans Bethe and Van Black, put forwarded the crystal field theory in 1929 and 1935. Now, what is crystal field theory? If we say it is a model, what it tells about somewhat orbital degeneracies, breaking of orbital degeneracies, and it is purely electrostatic interactions between the ligands and the metal ions. And this theory say only about d block complexes, only d orbitals, no s and p orbitals are taken into considerations. And this theory is based on two assumptions. Number one, the interactions between the metal ion and the ligands is purely electrostatic in nature, and the ligands are treated as a negative point charges or point dipole. Now, before going to discuss the crystal field theory, first we need to know what is the shape of d orbitals and what are the lobes. The lobes are in which directions, in which axis. So we know that there are 5 d orbitals, and among these, two orbitals, that is called dx square minus y square and dz square, are in along the axis. That means the x square minus y square is along x and y directions, the lobes are along x and y directions, and the lobes of dz square orbital is along z axis. And other three d orbitals, that is called dxy, dyz and dzx, are the lobes are in between the axes. Suppose we have a crystal octahedral field. First we have a metal cation Mn plus. All the 5 d orbitals are degenerate. When 6 ligands are approaching to the metal ion, it forms a spherical cloud of negative charge, and this negative charges is distributed uniformly over the surface of a sphere as shown in the diagram. Now, when the ligands are at the vertices, 6 vertices of the octahedron, then what happen? The orbital which are along the axis, that is x square, dx square minus y square and dz square, the interaction energy will be more. That means electrostatic repulsion will be more. Therefore, it gain energy, and its energy will be raised. And the orbital which are in between the axis, so there is no ligands are approaching, so there will be the energy will be less. So dxy, dxz, dyz, these 3 orbitals become orbital energy become less. Okay, and these 2 orbitals, upper and higher energy level orbitals, are termed as Eg, and these 3 orbitals is termed as T2z, right? And the separation between these two Eg and T2z level is called crystal field splitting energy in octahedral field, that is delta O. Okay, so this is the thing why there is a splitting of d orbitals, why there is a breaking of degeneracies of the 5 d orbitals. Okay, So next thing is that if we see the what is the separations. So this is the barycenter as you see in the left diagram. So it is same as that of the original d orbitals, where it is a free ion, no ligands are there, and the separation between the Eg and barycenter, it is 0.6 delta naught, or we can say 6 dq, and the separation between the barycenter and T2Z level is 0 minus 0.4 delta naught, or minus 4 dq. Now how the electrons occupy in these two energy levels, or you can say in these two orbitals. So the electrons follow Aufbau principle and Hund's rule of maximum multiplicity. So for D1 to D3 complexes, we got only the electrons occupy only T2Z levels, T2Z1 for D1, T2Z2 for D2, T2Z3 for D3 complexes. So the situation is somewhat different when we have D4 configurations. There will be two possibilities as shown in the figure. So either the 3 electrons occupy in T2Z level and the fourth one will occupy to the EZ levels, or all the 4 electron occupy in the T2Z levels. Now when we got these configurations, T2Z3 EZ1, and when we will get this configuration T2Z4 EZ0. So the case is that when the pairing energy is more than crystal field stabilization energies, or you can say when the pairing energy is more than the crystal field splitting energies, right, delta naught. So if pairing energy is more than delta naught, then then we will get the first one configuration, that means T2Z3 EZ1. And why? Delta naught value is less, that means the electron can move to the upper orbitals, higher energy orbital easy. If the crystal field splitting energy is more, so it cannot, the electron cannot move to the higher energy levels. Okay, and another thing you should remember that the pairing energy is more, that means more energy is needed to pair up the electrons. Pairing energy is less, means less amount of energy is needed to pair up the electrons. Similarly, for D5, D6 and D7 we get two possibilities, right, and it depends on the CFSE, or you can say crystal field splitting energies, and pairing energies. Now for D8, D9 and D10, these three configuration we get only one configurations, and it is same for both high and low spin complexes. There will be no other options. Okay, so we get only one configurations as we have shown in the figure. Now there are two terms, one is called weak field ligand, one is strong field ligand. What is this? So strong field ligand is that it creates large delta naught values, crystal field splitting energy is more in case of strong field ligand, and in case of weak field ligand the crystal field splitting energies, that means the separation between the EZ and T2Z level is small, and strong field ligands favor low spin complexes because the electron cannot move to the higher energy orbital easily, and weak field ligands favors high spin complexes as delta naught value is small, the electron can move easily to the higher energy orbitals. Now spectrochemical series, we need to remember in the left side the ligands are weak field ligand, and in the spectrochemical series, in the extreme light, these are strong field ligand. Okay, and strong field ligand, as we already told, strong field ligand creates delta naught value large, and weak field ligand creates the delta naught value less. Now let us consider two complexes, hexamine cobalt 3 plus and hexafluorocobalt 3 plus. So both, if we see, both the complexes are octahedral, both the complexes containing same metal cobalt, both the complexes has a plus 3 oxidation state of the metal. Now only difference is that ligands are different, and first one shows diamagnetic low spin complexes, and the second one is a high spin complexes, and it is paramagnetic in nature. Why? Because in the first case, ammonia, not ammonia, amine. So ammonia is a strong field ligand, so it creates delta naught value high. So basically it favors low spin complexes. All the 6d electron, cobalt 3 plus means d6, all the 6 electrons occupy in T2Z levels and all are paired, so it is diamagnetic. But in case of fluoride, so fluoride is a weak field ligand, delta naught value is small, so the electrons will move to the EZ level easily, and it favors high spin complexes. So if we see, there will be 4 unpaired electrons, and therefore it is a paramagnetic in nature. Now CFSE, crystal field stabilization energy, what is that? So from this we can say how much energy is stabilized. This configuration is how much stabilized. Okay, so if an electron is occupying to T2Z levels, that means that amount of energy is stabilized, and if an electron is occupying in the EZ level, that much amount of energy is destabilizing the complex. And how we calculate the CFSE? By this we can calculate this CFSE from this formula. So CFSE is equal to minus 0.4 x plus 0.6 y delta naught. X means what? X means is number of electrons in T2Z orbitals, y means number of electrons in EZ orbitals. If we see, so this is the in octahedral crystal field, splitting of a d or electrons, d orbitals you can say, in octahedral field. So if we say this is 10 dq, upper one separation between the EZ and beryllium, there is a 6 dq, and lower one is minus 4 dq, and if we express in delta naught, so it will be upper one will be 0.6 delta naught, lower one will be minus 0.4 delta naught. Now we have to calculate the CFSE for different configurations, right? So for D2 it will be just calculate 2 into 0.4 minus 0.8 delta naught. For D3 configuration, it is written here minus 1.2 delta naught. So for D4 it will be two possibilities. Okay, one will be T2Z3 EZ1, so delta naught will be minus 0.6 delta naught, and for T2Z4 EZ0 it will be minus 1.6 delta naught. Now overall stabilization energy will be CFSE plus pairing energies. Okay, so overall stabilization energy will be CFSE plus PE. Now in these configurations it will be minus 1.6 delta naught, and one pairing is there, so plus P we should write. Now if the delta naught is less than P, pairing energy, then the upper EZ orbital is occupying to minimize the pairing energy. Okay, and it is a high spin case. If delta naught is greater than that of pairing energies, then T2Z orbital will be occupied, and it gives a low spin complexes. And pairing energy for a particular element is fixed. and therefore the configuration is only depend on the values of delta naught. Okay. So, if we see in different configuration the crystal field stabilization energies, for D1 what will be the CFAC, okay, D1 it will be minus 0.4, D1, D2, D3, so only we get only one possibilities, and D8, D9, D10 we get one possibilities, and the crystal field stabilization energy is given. But for D4, D5, D6 and D7 we have already told that there will be two possibilities depending upon the pairing energy and delta naught. It will be high spin or it will be low spin, and for high spin what will be the crystal field stabilization energy, and for low spin what will be the crystal field stabilization energies. So, okay, this